Hello, my name is Neeraj. My student ID is BSCP CS63134, and this is the task 9.3D for module SIT111. So in this task, I'll be explaining how to translate the given CPU implementation diagram to a CPU HDL code. So first, let us look at the provided diagram. This is the CPU architecture. This diagram represents the proposed design for a CPU architecture that I will use to explain and implement the CPU's HDL code. The CPU is made up of a number of logic gates, including a multiplexer, ALU, A register, and D register. This is the key components and input and outputs of the devices inside the CPU. So that we have discussed so far. So the main question is how to interconnect them to make the CPU operate as required. So for that, let's take a look at the main implementation, which was shown in the first slide as well. This image is a schematic diagram of a CPU architecture. It shows various components and their connections, including decode, ALU output, outem, writem, addressem, and a program counter. The instruction input is connected to the decode block that interprets the instruction. There are three primary input labeled as instruction in and reset. The arithmetic logical unit is the central in this architecture, with inputs from A register, D register, and M register. There are several control bits around the ALU that determines its operation based on the decoded instruction. Output include ALU output, outem, which appears to be the data output, and writem for writing data into memory, addressem for memory addressing, and program PC for the program counter updates. Now that we have identified the inputs and outputs of the CPU architecture, we can now implement the code of the CPU and discuss how it works. So I'll show you the code of the whole CPU HDL so that I can break it down and explain it, which would be easy to explain and understand how the code works. So this is the code that I implemented for the CPU.hdl. So we can see that this is the CPU and it has all these codes available. So as mentioned before, I'll break these down into parts and explain it for better understanding. So this is the first part of the code which I'll be explaining. This is the header section. So these lines define the inputs and outputs to the CPU. The in-M is the in-value input, instruction is the instruction for execution, and reset is a signal to either restart or continue the current program. The outem is the M value output, writem is a flag indicating whether to write to M, and my address M is the addressing data memory of M, and T's program counter is the address of the next instruction. So if you see this code line by line, the in part of the code, the input, this line declares the input pins of the chips. First one is this 16-bit input memory, the second one is the 16-bit instruction input, and the third one is the reset signal, whether to restart the program or continue executing the current program based on the conditions. The output part of the program, this line declares the output pins of the chip, which includes the 16-bit output for memory and a writem for write signal for memory, and address M, which is the 15-bit output representing the address in data memory, and the program counter, which is a 15-bit output representing the program counter. Now this is the first part of the section in the CPU HDL code. We have now 4 different gates available in this: the AND gate, OR gate, mux 16K, and the D register and A registers. So first, so these gates allow the CPU to function and perform specific operations. So first, there are two types of instruction coming into the CPU from the instruction memory. These are the C and A instruction. So if we see in the A instruction, this has a symbolic syntax of add value, and this value can either be a number that it's decimal, non-negative, or symbol. If the value of the instruction is a number, then the section will set the contents of the register to the specified value in the instruction. If the value of the instruction is a symbol, the instruction will set the contents of the register to the value at where the symbol points to, and this value will not be the actual value in the end register. On the other hand, the C instructions have a symbolic syntax of dest equal to comp and jump. This instruction performs the computation on the CPU, which is stored into the destination register or a memory location. It can also tell us that the CPU will jump to another instruction memory address status pointed by the value of the symbol. So coming back to the code, let us first look at the first two lines of the code. So those two lines determine the type of instruction. If the 15th bit of the instruction is 0, it's an A instruction, and if it's 1, it's a C instruction. So the first line, the not in instruction 15 and out A instruction, it inverts the most significant bit of the instruction input and stores the result in A instruction. The second line inverts the value of A instruction and stores the result in the C instruction. So going to the second part, like third and fourth line, these lines check the destination of the C instruction in the A register. If it is like if the output of the ALU is selected as the input to the A register. So the first line, the AND gate performs a bitwise AND operation between C instruction and the 6th bit of instruction, storing the result to ALU to A. And the second line, the mux16, chooses between the entire instruction and the ALU output based on the value of ALU to A, storing the result in the A regi. The third part, the 5th and 6th line, this line loads the A register if the instruction is an A instruction or if the destination of the C instruction is the A register. So the OR gate performs a bitwise OR operation between A instruction and ALU to A, storing the result in load A. The A register updates A register based on the input A region and the load signal load A. The 7th line, the mux16, this line selects either the A register output or the M input based on the A bit of the instruction. So it chooses between the A register output, the A out, and the memory input in M based on the 13th bit of instruction, storing the result in A M out. Now looking at the 8th and 9th lines, these lines load the D register from the ALU if the instruction is a C instruction and the destination is the D register. The AND line performs a bitwise AND operation between C instruction and the 5th bit of the instruction, storing the result in load D. On the D register, last line, updates the D register based on the input ALU out and the load signal load D. Now if we take a look at these code, this is also like a continuation. The ALU part, the first part, this line performs the ALU operation based on the D register output, the selected A or M value, and the control bits of the instruction. And the second part sets outputs for writing memory. So these lines sets outputs for writing to memory. The address M output is set to the A register output. The out M output is set to the ALU output, and the write M output is set if the instruction is a C instruction and the destination is N. So if we take a look at line by line, the first line O16, it performs a bitwise OR operation between the false and A out, storing the result in address M, setting the least significant bit of address M to 0. The second OR gate or code performs a bitwise OR operation between false and ALU out, storing the result in out M, setting the least significant bit of out M to 0. Now the third part, the AND gate, performs a bitwise AND operation between C instruction and the fourth bit of instruction, storing the result in right M. Now coming to the last part of the code, these lines calculate whether to load the PC program counter with the A register or increment the program counter. This is based on the jump bits of the instruction and the 0 and negative flags from the ALU. So if we take a look at line by line, the first line, the AND line checks if the 0 flag is set ZR out, and the second bit of the instruction is 1, storing the result in JEQ. And the second line, the second AND here, it checks if the negative flag is set NG out, and the third bit of the instruction is 1, storing the result in JLT. Now looking at the third line, the OR gate here performs a bitwise OR operation between ZR out and NG out, storing the result in 0 or negative, something like that. Now if we take a look at the NOT gate, the fourth line in here, it inverts the value of 0 or neg and stores the result in positive. The fifth line, AND gate, this line checks if positive is true and least significant bit of instruction is 1, storing the result in JGT. And the sixth line, OR gate, it performs a bitwise OR operation between JEQ and JLT, storing the result in JLE. And the next line, the next OR line, performs a bitwise operation between JLE and JGT, storing the result in jump to A. Now coming to the last three lines, the first one, the AND gate, it also performs a bitwise AND operation between C instruction and jump to A, storing the result in PC load. The next line, the NOT gate, it inverts the value of PC load and stores the result in PC inc. Only inc if not load. So the last, now coming to the last line of the code, the PC, which updates the program counter based on the inputs A out, PC inc, PC load, and resets, storing the result in PC. So this is the end of the code. This is how I implemented the CPU.htl code by translating the given diagram into an HTML code. So this is how I understood and did it. So that's all from me now. Thank you.